Hey IB environmental students, this is a review of pyramids. There's three major types of pyramids: energy, numbers, and biomass. And we're going to go through each of those and kind of compare the pros and the cons of each. And if we want to look at our objectives, we're going over these are them. Let's get started. So the first type of pyramid we're going to do is the pyramid of energy or productivity. We're going to think about this sometimes as kilocalories, maybe in watts or in joules, but just for the purposes here, this one says units. That's okay. We know that there's energy units, but we can really quickly see that only 10% of the energy from one bottom trophic level moves to the next higher level trophic level, and that's why we get, that pyramid shape that's narrowing in at the top. And we know that's happening because of the second law of thermodynamics, where 90% is lost as disorder, entropy, right? And we know that that's very much heat, a lot of it. So some of the good things about this type of pyramid are that it shows great information. How much energy is at this trophic level to support the next one and the next one and the next one. And that might change over time, so we could compare different energy pyramids at different times of the year or different seasons. So it clearly shows what we're going to think about as a stock hold of an amount of energy that's hidden in these organisms at any given period of time. We know that productivity for producers is primary productivity. We know for upper level consumers it's secondary productivity. But some of the disadvantages are that this is hard to measure. Going out there and learning not only just how much energy is being gross primary productivity for the algae, but also include the phytoplankton to get a better picture of that whole first trophic level. That's going to be crazy to measure. So this one's tough, but it's very beneficial to analyze. Compared to numbers, which is just going to be how many organisms are at each trophic level. We talked about in class that it's hard to guess which way we should measure number of organisms. So like for grass, we can measure clumps of grass. We can measure in number of blades of grass. Blades would really represent how much photosynthesis is happening. We talked in class about leaves, number of leaves on a tree versus number of trees. And the green area is really the area that's doing the photosynthesis. But this could be hard to measure, so we do have to kind of balance with ease with how much information this is going to provide us. For these bigger moving creatures, we could do Lincoln Index and estimate population size. So overall, it could be pretty easy to collect this data compared to the pyramid of energy. However, it's less useful, right? It doesn't tell me how big the organism is. I could have 10 mice. That's going to be not that much matter that I'm referring to. 10 mice. I could probably hold 10 mice in my arms if they didn't run away from me. However, if I were talking about 10 whales, I can't hold 10 whales in my arms. So this doesn't take into account size at all. It also doesn't take into account how much energy is really held up in each of these organisms. And that would be more pyramid of numbers. Pyramid of energy, which we previously just did. But what we can see is easy to collect data for the most part, other than counting blades of grass, which we probably wouldn't do. We would do clumps. And we can easily see how this also, just like the other one, narrows out, and that's because about 90% of the biomass is lost as well at each trophic level, and we do need to have more producers at the bottom in order to support the next levels on the trophic levels on the pyramid. However, sometimes we do see an inverted pyramid, and an inverted pyramid would refer to an almost upside down looking pyramid compared to this one we just looked at, and that would be things that are living in a habitat that's just one organism, like a big dead tree, but there's so many organisms living in it. So we only have one producer that produced all that original energy, that net primary productivity, right? This tree would originally get, but there's so many other organisms living in it. So this is an inverted pyramid. We don't talk about this much, but just good to know. The question we've all been waiting for: what in the world is biomass? This class has been referring to it, but what really is it? So it's the mass of the organic material in an organism or in an ecosystem, usually per unit area. That's going to be really related to gross productivity, right? Gross secondary, gross primary productivity. And it's really interrelated. We usually think about it as dry weight biomass. Think about a watermelon. A watermelon is mostly what? Water. And we wouldn't really get a good sense of how much matter was taken in through the process of photosynthesis if we included water in that because it would be an unfair calculation to compare that with a sunflower, which doesn't really hold or retain that much water. So we usually take that out, and the way we would take out the water when we do dry biomass is we would unfortunately have to kill the organism. Like we would take a whole clump of grass and we would then put it in a little tray and put it in an oven and let it dry slowly so we didn't burn it and just the water evaporated out. Just thinking about that, though, that's not that bad when we talk about grass and plants, but when we think about bigger plants like trees, it's very hard to, cut a whole tree and slowly take out the water. Similarly, thinking about killing an animal in order to dry it out is not very ethical. So we kind of have to do our best with that. So we can't always do dry biomass, but we try to, especially when we think about plants. So let's look at this pyramid now. So the pyramid of biomass is going to show us a very similar trend, and it's going to look almost exactly the same 10% rule as we've been seeing in all of the other pyramids we've been looking at. So the 10% rule really doesn't always just refer to energy, but it could refer to amount of biomass between trophic levels as well. Remember that this is a mass over a certain area per unit time. So the pro is it takes into account size. So I could compare a whale and it would take into account the fact that the whale was large compared to some other smaller organism like a jellyfish. But it's really difficult to measure, to collect a bunch of trees or a bunch of whales, and then it could be tough depending on if the conditions in the area change. It might change the size really quickly of the organism. We know that things wilt in different conditions and that sort of thing. So overall, we think this is a pretty useful piece of information, but the best part is it takes into account the size. So let's just review. We've been talking about stocks, but we're not really defining it, right? So a stock is a place where mass or matter is held, whether it's water or just carbon-based organic material. And storage pretty much means the same exact thing. They're synonyms. So a pyramid of biomass and a pyramid of numbers show momentary stock of organic matter. How many organisms are in the environment? That's going to be a stock of carbon and lots of different nutrients. And same thing with biomass. How much organic matter was taken in either by photosynthesis or through eating? That gross primary productivity or that gross secondary productivity. The pyramid of energy is going to really show the rate at which that was taken in. This is more referring to time a little bit better than others. This slide here is really kind of complicated. Would I really expect us to understand this through and through? No. But if you're getting a sense a little bit better of stocks and storages, that there are areas where we hold matter, that makes me happy. Okay, so stocks and storages are areas where we hold matter, whether it's biomass or we can look at it more just the number of organisms or how much energy they're taking in per unit time. Just last reviewing topic 2.1.5. This idea of chemicals entering the pyramid and what that does. So we talked in class about Minamata Bay, which was a methyl mercury contamination in Japan. And later in the year, we'll really focus in on this chemical DDT, which is pictured here, that affects this food web. And we really see the impacts of it at the top. Why? Because the top level consumer really gets a higher concentration of whatever chemical we're referring to in this idea of biomagnification and bioaccumulation. The idea of the top level consumer getting the brunt of the toxin is biomagnification, a magnifying of the concentration. We can remember a magnifying of the concentration happens at the top of the food chain. That's biomagnification. More methylmercury or more DDT will impact the top level carnivore. Compared to bioaccumulation refers to just the fact that organisms are going to be exposed to the contaminant and they're not going to be able to poop or pee it out. That's just it entering the system in general. So just practice comparing these two words. You're going to need to know the case study Minamata Bay, and we'll get to DDT next. And that's it. IB Environmental. Good job reviewing.